Hello, guys. So you're welcome to this lecture. This is a continuation of the previous one where we defined what a subspace is, and then we did a few examples, just two simple examples. In this lecture, I want to do a couple of more examples on subspaces. Okay. So let me just remind you of a critical theorem that we applied, right? To show that something is a subspace. Theorem 7 is very important to show that a subset, say W, is a subspace of a vector space V. You pick any two vectors. So vectors here, elements in W, and show that when you add them, the result is in W, right? So addition is closed under W. And then the scalar multiplication is closed as well. So if I take an element or a vector in W multiplied by scalar, the result is also in W. Okay, so once you're able to show these two, then you can conclude that the subset W here is a subspace of the vector space V. Okay, so let's go and do some more examples of this. So here you're given here, we want to determine whether the set S, all right, the set S is a subspace of R3, okay, under the usual vector addition and scalar multiplication. Okay, so we'll take the first one and then the second one. Well, so for the first one, we have S is equal to X, Y, and Z, such that X minus 2Y plus Z is equal to 3. Okay. Now this is a subset. Let me just show this. This is a subset of R3 because without I think I explained this already, right? Without this condition, right? Without this condition here, S will just be R3, right? Because X, Y, and Z could take any real number, could take any number, and that will be R3. But this condition restricts this. Okay, so that is why it is a subset of R3. Okay, good. Now, how do we show that it is a subspace or is not a subspace? Well, you could go and check the two conditions for of the theorem, but here is actually much easier than that. Observe that the zero vector is not, and that is one of the easiest one you should check. Okay, here you notice that the zero vector is not in S. If I pick 0, 0, and 0, this condition will not be satisfied. You see, if I pick 0, 0, 0, I'm going to have 0 minus 2 times 0 plus 0, which is 0, but 0 is not equal to 3. So if I pick the zero vector, this condition is not satisfied, which means the zero vector is not an element of this. So 0 is not an element of S. So straight away, you can just conclude that S is not a subspace of R3. Okay, without checking, checking the addition and all of that. Okay, good. Now let's go to the second one. The second one, you will notice that 0, 0, is an element of S, right? If I plug in 0, 0, 0, I get 0. So that is fine. So now that we have done the easy check, we can go back and then actually apply the theorem. Okay, we pick two elements as we've done before. Pick two elements in S, and then show that the sum is also in S or is not. Okay, and then do that for scalar multiplication as well. So let U and V be elements of S. So we can let U be, for instance, X1, Y1, Z1. We can let V be X2, Y2, Z2. But if U is an element of S, then we require it to satisfy this condition, right? Okay, it must obey this this rule here. So if U here is an S, then I expect that X1 minus 2Y1 plus Z1 has to be equal to 0, right? Because of this. And since V is also in S, this must be true. X2 minus 2Y2 plus Z2 must be equal to 0. Okay. So all of this, everything here is basically showing that U and V are elements of what? Of S. Now we go back and then we show that the sum is an element of S, and the scalar multiplication is also an element of S. Okay, so we do U plus V. U plus V will be this plus that, of course. Addition of vectors, you have x1 plus x2, that will give you this. Y1 plus y2 will give you that, and z1 plus z2 will give you this. So this is the sum. Well, for U plus V to be an element of S, this rule must hold, right? This thing must be satisfied, this rule here. Okay, so what that means is that if I take x1 plus x2 minus 2 times y1 plus y2 plus z1 plus z2, if I'm able to show that that is equal to 0, then I have shown that U plus V belongs to S, is an element of S, and therefore, right, the first condition is satisfied. Okay, so that's what we're going to do. So we're going to take U plus V, these elements here, plug them into something like this and show that is 0. Okay, good. So I take the first element minus twice the second element plus the third one. Okay, I can expand this, and I'm going to have x1 plus x2 minus 2y1 minus 2y2 plus z1 plus z2. Well, I can rearrange this and write x1 minus 2y1 plus z1, and that gives me this guy here, and then rearrange the other ones to get that. But remember that this guy here is 0 because these are the elements from U1. Okay, so this guy is equal to 0. Also note that this guy is also 0. Okay, so this is 0, and that is 0. 0 plus 0 is 0. So what this means is that U plus V here is an element of S, belongs to S. Okay, good. Then the second condition to test is to show that scalar multiplication is closed, it's also in S, right? So I take a scalar lambda multiplied by U, I have lambda times U. Of course, you multiply each component by lambda, you get this. Well, for lambda U to be an element of S, this rule again must be satisfied, right? I take the first element minus twice the second element plus the third one. If I can show that is equal to 0, then lambda U is an element of S, right? So I do the same thing. So I take the first element minus twice the second element plus the third one. This, I can rewrite it. I can factorize lambda out. But again, this guy is 0 if you go back, right? We have shown that this is 0. So this is 0. So I'm going to have lambda times 0, which is equal to 0. Okay. Therefore, lambda U here is an element of S. So the two conditions are satisfied. Vector addition, scalar multiplication are satisfied. Therefore, I can conclude that S is a subspace of R3. Okay, then you have that. Okay, so go through this and then just do it yourself. Okay, and then convince yourself. Okay. We're going to do another one here. Here we're going to look at matrices instead of vectors in R3 or R2. Now here we want to determine whether the set H, so this is actually subset H here, is a subspace of M to 2 under the usual matrix addition and scalar multiplication. So again, this is what you have. Again, it's a subset because of these conditions. So H is a set of 2 by 2 matrices, but there are 2 by 2 matrices that must obey this rule. The sum of the diagonal elements is 0, and B minus 2C here must also be 0. Okay, so if I pick any element in H, this must be true and this must be true before I can say that that element is an element of H. Okay, so how do we prove that? Well, similar to what we've done already, we pick two elements and show that the sum is also in H, and show that if I take an element multiplied by a scalar, that product is also in H. So let U be an element of H. Let it be this A1, B1, C1, D1. Let V be given by this. Okay. Now, if U here is an element of H, right? If U is an element of H, then its elements, right? The entries here must obey this. So from U, we get that A1 plus D1 has to be 0, and B1 minus 2C1 has to be 0. And if I take V, I expect that A2 plus D2 is 0, B2 minus 2C2 must be 0. Okay, Again, all of this, we haven't done anything yet. We haven't started showing that it's a subspace. All we've done is that I picked two elements, and this is what shows that these two elements are in H. That is all we've done so far. Okay, so the next thing is actually show that H is a subspace, right? So we add these two elements and show that the sum, okay, the elements of the sum obey these rules. If they do obey this rule, then, all right, these equations, if they do obey them, then of course the sum is an element of H. So that's what we're going to do. So take U plus V, sorry, and you have this, right? U and V, you're adding them. So you add the entries. A1 adds to A2, B1 to B2, C1 to C2, D1 to D2, and that gives you that, okay? So for U plus V to be an element of H, the sum of the diagonal must be 0. And if I take this element here minus twice this guy, I should also get 0. Okay, so let's do the diagonal first. This plus that would be A1 plus A2 plus D1 plus D2. I can rewrite this as A1 plus D1, right? And A2 plus D2. But this guy is 0, and that is 0, right? From here, A1 plus D1 is 0, and A2 plus D2 is 0. Okay, this is also 0. Therefore, this is 0, and that is 0. 0 plus 0 is 0. Okay, that shows that the diagonal elements of U plus V is 0. Okay, then we do the off diagonal ones. We take this guy minus twice of this. So B1 plus B2 minus twice of C1 plus C2. Again, I can expand this. I have this. I can rewrite it as B1 minus 2C1 plus B2 minus 2C2. Again, this is 0, right? And that is 0 if you go back. This is 0, right? And that is 0 because U and V are elements of H, okay? And so this is 0, that's 0, 0 plus 0 is 0. Therefore, the off-diagonal elements also go to 0 if you do this, okay? So all of this and that shows that U plus V is an element of H, belongs to H, okay? So that is the first one. The second one is take a scalar, let K be any real number, okay? You can use lambda, you can use C, whatever. So let it be K, multiply K by U. You could have used V. So if you multiply K by U, you're going to get this, right? It's a matrix, so you multiply each entry by K, and you have that, okay? Again, to show that this guy belongs to H, is an element of H, we have to show that the sum of the diagonal is 0, and then this guy minus twice of this is 0. If we show that, then of course this is an element of H, okay? So we take K1, KA1 plus KD1, right? Sum of the diagonals. This is equal to, I can factorize K out, but this is 0, right? So I have K times 0 is equal to 0. And then I take this minus twice of this, right? I can factorize K out again. This guy is 0, so I have K times this is 0, okay? So this shows that K times U here is an element of H. So both conditions are satisfied. Therefore, I can conclude that H is a subspace of the set of 2 by 2 matrices. Okay. Okay, good. So that is basically the procedure. You get the gist of the approach. You just apply the theorem and apply the two conditions. Again, in this case, it was easy to see that 0, 0 is an element, right? It's an element of H. Okay. If this is 0, that's 0, that's 0. These conditions will be satisfied, right? 0 plus 0 is 0. 0 minus 2 times 0 is 0. Okay. So the 0, 0 is an element of H. So if, for instance, this was 1, right? If this was A plus D is equal to 1, then we can see that 0, 0 will not be an element of H, and therefore it will not be a subspace. You see that? Or if this guy was 1, right? Or 2, or some other number. Okay. Then we could have concluded straight away without this, all this expending energy here. We could have concluded straight away that that H is not a subspace if this was 1 or some other number apart from 0. Because 0, 0, the 0 vector, in other words, the zero matrix is not an element of H, and therefore it's not a subspace. Okay, good. Sometimes, okay, sometimes you are given, let me do this. Sometimes you are given diagrams, all right? And from there you can actually show, you can actually determine whether a given subset of R2, let me erase, clear this. Sometimes you can be given a subset of R2. So for instance, let's take some subset here. Take this this set, H or S or something. Okay, this is an R2, X, Y. Okay, so each here is in the first quadrant with some elements in it, some vectors. So the point is H a subspace of R2? Is it a subspace of R2? Okay, so you think about it a little bit. Remember, one of the things I mentioned that you should always check first, which is an easy check to do, is to see whether the zero vector or the zero element is part of the subset. Okay, so in this case, you see this guy is in the first quadrant, but it does not intersect the zero, so zero is not part of it. So straight away you can see that H is not a subspace, right? Because zero is not an element of H. You see that? So that's one of the easiest one you can check. Okay, the other one you can let me erase some of these. The other one that you can check is this. Suppose that now instead of this, you are giving another subspace. Suppose that we still have a subset here, but this one includes so this one includes a zero. So this is from here and then from up to there. This is zero. So let it be H or S, another subset in R2. Okay, this is X and Y. Okay, so the question is, will this subset here in the first quadrant, will it be a subspace of R2? Okay, so you think about it a bit. Note that to be a subspace basically also means that you are a vector space. If you're a subspace, you're a vector space. The only point is that you are a subset, okay, of a bigger set. All right. So all the rules, the axioms for a vector space also apply to the subspace. Don't forget that. Okay. So one thing you will notice here is that I can take in R2, I can pick a vector. Let's call it, you know, V or something, right? I can take a vector here. Okay. Now, if I pick elements here, all as I said before, all the axioms, all the properties for a vector space must apply to here. Okay. So remember that for a vector space, we need it to be what is it? We need it to be an abelian group, right? With regards to addition. So each here has to be an abelian group. For it to be an abelian group, associativity must hold. That's fine. There must be an identity element. In this case, we need zero to be an element of H. Zero is an element of H. That's fine. If I pick a vector in H, okay. If I pick an element in H, it must have a negative, right? It must have an additive inverse. Negative V must also belong to H. Now, if the vector V is this vector, the negative V is a vector that is going in this direction, right? This would be the vector negative V. But negative V here is in the third quadrant, okay? Negative V is not inside the first quadrant. And therefore, negative V does not belong to H. And therefore, this subset here as drawn is not a subspace of R2 because there's no additive inverse, for instance, for this vector here. Okay, so that is how you should think about vector spaces. So you can apply the two conditions from the theorem to show that something is a subspace, but to show that it is not a subspace, go back to all the axioms for a vector space and make sure they are satisfied. Or if one of them is violated, then you can easily conclude that it is not a subspace. Okay, so there are several examples of this nature that you can often look at. Okay, good. So I think I will end here. There are some exercises that you could try. W here, this is a subset of the 2x3 matrices, right? You want to show whether it's a subspace. Here, you want to show whether this polynomials is a subspace of P3. Note that A is A here, this is B, this is B. In P3, A, B, C, D, right? The coefficients here will be different. But here is a subset, right? This is a subset of the set of polynomials of order 3 because you have A here, you have B and B here. So check whether this is a subspace. And then you can do the same thing for this 2x2 matrix. Then the last two examples, check, this is similar to the other examples we did before. Check whether this is a subspace, right? You have 2x, 3x, and negative x, where x is any arbitrary number, real number. And here you are given the subset. You want to check whether this is a subspace of R3. Okay, so try this once. I'll end it here. When we come, the next video will look at linear combinations and linear dependence and independence. Okay. Okay, good.